In this section, we expand on what we've learned already with arithmetic sequences and begin working with another type of sequences called a geometric sequence. So when you're looking at a geometric sequence, we're not looking for a common difference now, we would be looking for a common ratio. Ratio, of course, is going to be making fractions or dividing one number by another. So as we did with arithmetic sequences, in geometric sequences we're comparing a term to the term before it. So if I take the second term and divide it by the first term, and I take the third term and divide it by the second term, you'll notice 6 divided by 3 was 2, 12 divided by 6 is 2. In this case we have a common ratio. So with the common difference we were subtracting the first term from the second term. Here we're dividing the second term by the first term. So here 68 divided by 136, that's equal to 1/2. 34 divided by 68, that's equal to 1/2. So I've got the same ratio between the numbers. My common ratio is 1/2. So when you're checking sequences for what type they are, as we move out of the sections where they're pre-identified for you, you'll need to be able to identify and tell one sequence from another. First, you might check for a common difference. If you don't find a common difference, you might check for a common ratio. Sometimes spending a little time just looking at the sequence ahead of time will allow you to do that without doing a lot of math. Right, so here's an example of that type of problem, just identifying, is it geometric, arithmetic, or neither? So if I check here to see if it's arithmetic, 3 minus 1 is 2, 7 minus 3 is 4, so this is not arithmetic. I don't have a common difference. Right? 3 divided by 1 is 3, 7 divided by 3 is 7/3, but it's obviously not 3, so I don't have a common ratio, so this one would be neither. -7 divided by -11, I'm checking for the ratio first, and you can see that -3 divided by -7, that's not going to be a common ratio either. That's not going to work. -7 minus -11 is 4. -3 minus -7 is 4. So I have a common difference. This one is arithmetic. My common difference is 4. So if I have 3/2 divided by 1/2, that means invert and multiply. That becomes 3. I'd have 9/2 divided by 3/2. That also equals 3. I have a common ratio. This one is geometric. Okay, so if I have a common difference, it's arithmetic. If I find a common ratio, it's geometric. If I don't find either of those things, then it would be neither. An explicit rule, as we learned also in arithmetic sequences, relates each term to its place in the sequence. So it allows me to find a term based on knowing its place in the sequence. And this is what the explicit rule for a geometric sequence would look like. They are exponential functions, right? And you can see that to find it, I need to know the first term and the common ratio, much like in an arithmetic sequence where I needed to know the first term and the common difference. So you can see 10 divided by 5 is 2, 20 divided by 10 is 2. My common ratio here is 2. -5/3 divided by 5 is going to be -1/3. 5/9 divided by -5/3, invert and multiply, right? That becomes -1/3. So my common ratio is -1/3. If I take the first term and the common ratio and plug these in, I know that a sub n will be equal to a sub 1, which is 5, times my common ratio, 2, to the n minus 1 power. This is my explicit rule. Over here I know that a sub n is equal to my first term, 5, times my common ratio, negative 1/3, to the n minus 1 power. Okay, so that's how we write the explicit rule. We use this formula. We have to identify a sub 1 and r, the common ratio, in order to do this. Notice here that the first term, the 5, and the common ratio, 2, cannot be multiplied. Order of operations stops the multiplication because we must do exponent before multiplication. And this variable n stops us from doing exponent first. Okay, we can also use this equation to find the rule using any term in the common ratio. If I don't happen to have the first term, then I can plug these guys into this formula. Here I have that a sub 3 is equal to 72, so I know that 72 will be equal to a sub 1, which I don't know, times my common ratio, 6, to the n, right? N in this case was 3, minus 1 power. So I know that 72 will be equal to a sub 1 times 6. 3 minus 1 is 2. 6 squared, which is 36. 72 divided by 36 is equal to a sub 1. So I know that a sub 1 is equal to 2. If I step back now and write the rule, I know that a sub n is equal to the first term, 2, times the common ratio, 6, to the n minus 1 power, and now I've written the rule. So as with any formula, if I'm supplied all the parts but one, I can find the missing part. So in this case, I didn't have a sub 1, but I did have a sub 3. I know that n was 3 and r was 6. I plug those in for a sub n, r, and n, and it allows me to find a sub 1. Okay? And similarly, I can put together a system by using two different terms, knowing their places. So I know that negative 20 would be equal to a sub 1 times r to the 2 minus 1 power. Right? And if I simplify that, negative 20 is equal to a sub 1 times r to the first power. 2 minus 1 is 1, a times r. Okay, and then I do it again. Negative 5 is equal to a sub 1 times r to the 4 minus 1 power. The 4 minus 1 will be 3, so if I have negative 5 is equal to a sub 1 times r cubed. Now if I solve and substitute, in this case I'm going to solve for a sub 1. Right? So if a sub 1 is equal to negative 20 divided by r, I take negative 20 divided by r and I plug it in for a sub 1. Negative 5 is equal to negative 20 over r times r cubed. Here I'll get that one to cancel with that one, so I get r squared. If I divide both sides by negative 20, I'll get negative 5 divided by negative 20 is equal to r squared. That means that r squared is equal to 1/4, so r will be equal to 1/2. Once I know what r is, I could plug it in up here, and I could find a sub 1, so negative 20 is equal to a sub 1 times 1/2. To get rid of the 1/2, I multiply both sides by 2, and I get that a sub 1 was equal to negative 40. And now I can write the rule because I have a sub 1 and r. So a sub n will be equal to a sub 1, negative 40, times r, 1/2, to the n minus 1 power. And there we go. Okay, so all sorts of different ways that they can supply me with information that I can then use this formula to derive the explicit rule for my sequence. Okay, we also want to find the sum of a geometric sequence. It's slightly different. we still know that the sum of n terms, so what we're talking about, we'll take the first term times 1 minus r to the n power over 1 minus r. So in this case, I want to find the sum of 10 terms, and I want to find the common ratio. 9 divided by 1 is 9. 81 divided by 9 is 9. So I can go ahead and put 9 in there. And then I have everything that I need. I know that the sum of 10 terms will be equal to my first term, which is 1, times 1 minus r, 1 minus 9 to the n power, 10th power, over 1 minus 9. Okay, if I go ahead and simplify this, I'll find the sum of the first 10 terms in this particular sequence. Right, so this will be equal to 1 times, I know my denominator will be negative 8, but I'm going to need to figure out the calculator, use a calculator to figure this part out. I don't know what 9 to the 10th power is. So if I use 9 to the 10th power, it's a very big number. I'm going to take one number off of that. 3, 4, 8, 6, 7, 8, 4, 0, 0. So it was 1 minus that number. So 435,848,050 ends up being my sum. Now at the same time, I can use the same formula to find n. How many terms is the sum? Does the sum reach for 820? So if I put 820 in as the sum, I know that will be equal to a sub 1, which is 1, times 1 minus my common ratio, 9, to the nth power over 1 minus 9. All right, so this becomes negative 8. Here I'll have 820 over negative 8 will be equal to 1 minus 9 to the nth power. Right? If I actually add 9 to the nth power to either side, I'll get 9 to the nth power is equal to 1 plus 820 divided by 8. So that's 102, and let's see, 0.5 plus 1, so this becomes 103.5. 9 to the nth power equals 103.5. And if I want to solve for n, n will be equal to a log base 9 of 103.5. I took a log base 9 of either side. I could use that as log of 103.5 divided by log of 9. And you could do that, finish that out on your calculator. Okay, finding a sum from summation notation. This references that I want to find the sum of the first 8 terms. I'm starting with the first term, going to the 8th term. I know that 5 is a sub 1. I know that 4 is the common ratio because I'm in my explicit rule. And I can simply take these items and plug them in. So I'm going to find the sum of 8 terms. That's going to be equal to a sub 1, which is 5, over 1 minus r, which is 4, to the nth power, which is 8, all over 1 minus r. Right? So I know that the sum of these 8 terms will be equal to 5 times, I know I'm going to have negative 3 down here, 1 minus 4 to the 8th power. So 4 to the 8th power is 65,536. So it's 1 minus 65,536. So this will be equal to 65,535 divided by 3, all times 5. So the sum of 8 terms is equal to 109,225. Okay, so certainly much faster than finding the 8 terms and adding them together.